Right, let's look at a few definitions and stuff, formulas that you need to know. We'll start off with NS, which is your synchronous speed, and it can be determined by the formula F is equal to NS times P over 60, where P is your pole pairs and NR is your rotational speed, and that is always less than your synchronous speed. Now that is a basic circuit diagram of a three-phase induction motor, where we have R, which is your rotor resistance at standstill. X naught is your rotor reactance at standstill. And X naught is 2 pi FL, where your F is your frequency and L is the inductance of the rotor. Then the impedance of the rotor ZR is equal to R rotor plus JSX naught. That is for the running condition. And then at starting, Z naught is R naught plus JX naught. ZR is your rotor impedance when running at a slip of S. Right, and there I said it stands still. And then the slip can be defined as NS minus NR times NS. Also, NR is equal to 1 minus S times NS. And then the rotor current is the rotor voltage divided by the rotor impedance. Now that there will be your rotor resistance, voltage of the rotor. And this is your input voltage. Right. Then let's look at a few examples there. Can you see the screen? Guys?
Yes, sir.
New share. Basic. Yeah, man.
So everything is stuck on my side.
Can you see the screen with the examples?
Yes, sir. Yes, we can see it.
Guys, can you see that?
Yes, sir.
Can you hear me, guys?
Yes, sir, we can hear you.
Ron? Ron, can you hear me?
Yes, sir, I can hear you clearly.
And you can see the screen?
Yes, I can also see the screen.
All right, guys, make a photocopy of this quickly, as we are going to go through them one by one. Now the first question says a slip ring induction motor runs at 290 revs per minute at full load when connected to a 50 Hz supply. Determine the number of poles and slip. Now, this is going to be. Oh man, what is this with this bloody thing? Okay. So normally we know that for one pole pair, NS is 60p. If it's NP over 60. Oh, come on. So if we have one pair, it's going to be 3000 divided by 1. That'll give us a speed of 3000 revs per minute. Now, if we times it by 10, then we will get 10 pole pairs is 300 revs per minute. So let's say then AS is 300 minus 290 divided by 300. That gives us 0.033. Now, if we look at the formula for determining the number of pole pairs, we can say NS is equal to 60F over P. And therefore, P will be 3000 divided by 300. That gives us 10 pole pairs. Right. And the second question says we have a stator of a 3-phase induction motor has 3 slots per pole per phase. If the frequency is 50 Hz, calculate the number of stator poles and the total number of slots on the stator, and also the speed of the rotating flux. Then let's look. Then we can say that the number of pole pairs is equal to G dash. And G dash is S, which is your number of slips divided by the number of poles divided by the number of phases. So here we have 3 pole pairs, and then S is G dash times 2P times M. And that gives us 3 times 6 times 3. That means we have 54 slots. And then the synchronous speed is going to be 3000 divided by 3. That is 1000 revs per minute. Can you see this? What is going on with this bloody thing?
We can see the screen, sir.
All right, I wonder what's going on here. All right, let's say a new share. Basic again. Oh, come on. Then question number 3. A 4-pole, 3-phase induction motor operates from a supply of the frequency of 50 Hz. Calculate the speed at which the magnetic field of the stator is rotating, the speed when the slip is 4%, and the frequency of the rotor current when the slip is 3%. And fourthly, the frequency of the rotor currents at standstill. All right. So, first of all, our synchronous speed is 60 times F over P. You'll notice the book keep on saying 120 F over big P. Here we have P, which is a pole pairs, therefore we have 60. So that's 3,000 divided by 2, which gives us 1,500 revs per minute. Now for a slip of 4%, then we can say that NR is NS minus 1 minus S, so that's 1,500 times 0.96. That gives us then 1,440 revs per minute. Then the frequency of the rotor at a slip of 3%, that's the slip times the frequency of the stator, 0.03 times 50, and that gives us 1.5 revs per second. You times it by 60, then you get 90 revs per minute. So at standstill, our slip is 1, and the frequency of the rotor is going to be 50 hertz. Right. Number 4. The induction, three-phase induction motor is wound for 4 poles and is supplied from a 50 hertz system. Calculate the synchronous speed, the rotor speed when the slip is 4%, and the rotor frequency when the rotor runs at 600 revs per minute. So there we have synchronous speed is 3,000 divided by 2. That gives us 1,500 revs per minute. Rotor speed 1500 times 1 minus 0.04, that gives us 1,440. And the slip then, when it's running at synchronous speed of 600 revs per minute, then we can calculate the slip. But it's not NS, it's the slip alone. It's 0.6. And therefore the rotor frequency is S times Fs, which is 30 hertz. Then, example 5, we have a 12-pole, 3-phase alternator driven at a speed of 500 revs per minute. Supplies the power to an 8-pole, 3-phase induction motor. If the slip of the motor at full load is 3%, calculate the full load speed.
We went to the 8 no? We went to the 8 project in 3. Forgot my Excel. I don't know if this belongs to who. I'm attending this subject, which.
So for the alternator, we can determine the frequency, which is NS times P over 60. That gives us 500 over times 6 times divided by 60, which gives us 50 hertz. Now for a motor, your synchronous speed is going to be 60 F over P. That gives us 750 revs per minute. And therefore the rotor speed at a slip of 3% is going to be 750 times 1 minus 0.03, which gives us 727.5 revs per minute. Then let's look at the torque developed by a motor. at the instant of starting. So E2 is a rotor EMF per phase at standstill. And then we have the rotor impedance at standstill. Now, they say it's a square root of R plus X squared. You can also calculate it R plus JX in the polar form. And then I2 is E over Z. And cos phi is R2 over Z2. Now, at standstill, we find that K is equal to E2 times I2 cos phi. If we substitute it in the formula there, then we get that it's Ke squared R2 over R2 squared plus X2 squared. So therefore, the torque then will be 3 over 2 pi ns times E squared R2 over R2 squared plus X2 squared. But that ns actually should be the small ns. So therefore, at the top should be 360 over 2 pi ns times 3 E squared R2 over R2 plus X2 squared.
Sir?
Yes.
Sorry, I just want to ask you a question at the previous example. Example number 5.
Mm-hmm.
Why did you say 6 times 500 divided by 60 and not 12 times 500 divided by 120?
Like I said, the Raja is using 620F over big P, where that's the number of total number of poles. I'm using 60F over number of pole pairs.
Oh, okay, thank you, sir.
All right. Then let's look at example 3.6 of a 3-phase 6. All right, probably a 3-phase induction motor having a star-connected rotor. There's an induced EMF of 80 volts between the slip rings at standstill on open circuit. The rotor has a resistance and reactance per phase of 1 plus and 4 ohms respectively. Calculate the current per phase and the power factor when the slip rings are short-circuited, and B, when the slip rings are connected to a star-connected rheostat of 3 ohms per phase. Now remember, when they say the voltage between the slip rings, then that is what we have. And that voltage there is 80 volts. But remember, that's line to line. So we must divide it by square root 3 to get the phase voltage. So therefore, that's 46.2. Your Z rotor is 1 plus J4, which gives us 4.123 at an angle of 76. So the current, ER over Z rotor, 46.2 divided by 4.123, angle 76, gives us a current of 11.205, angle minus 76 amps. So the power factor will be the cosine of the angle there, which is cosine of 76. That gives us 0.242 lagging. Let's look at another question. All right. Come on. A 3-phase 400 volt star connecting induction motor has a star connected rotor with a stator to rotor turns ratio of 6.5. The rotor resistance and standstill reactance per phase are 0.05 and 0.25 ohms respectively. What should the value be of the external resistance per phase to be inserted in the rotor circuit to obtain maximum torque at starting? And what will this current be? Now there's two things that's new here. Remember, the induction motor can be substituted by the circuit of a transformer, so that we have KT ratio, and we can refer the rotor to stator values as well. And then for maximum torque, the rotor impedance must be equal to the stator, to the rotor reactance. Okay. So there we have 400 volts divided by square root 3 to get it to per phase, and divide by KT gives us the rotor voltage, which is 35.53. So for maximum torque, the rotor resistance must be equal to the rotor reactance, which is 0.25. And then they want the external resistance, 0.25 minus 0.05, which is 0.2 ohms. That gives us a rotor impedance of 0.25 plus J0.25, which is 0.354 angle 45 degrees. So the rotor current is E rotor over Z rotor. That gives us 100.5 at an angle minus 45 degrees. Power factor, cosine of 45, that gives us 0.7071 lagging. Then let's do another one. And share. Question number 8. At a 1100 volt 50 hertz delta connected induction motor, star connected slip ring with a phase transformation of 3.8. The rotor resistance and standstill leakage reactance are 0.012 and 0.25 ohms per phase. Neglect stator impedance and magnetizing current, and determine the rotor current at the start with the slip ring short-circuited, rotor power factor at start, and the rotor current at 4% slip, and rotor power factor. And then the external resistance per phase required to obtain a starting current of 100 amp in the stator supply. Right, so what we're going to use now is the transformer equivalent circuit. So, all right, first of all, rotor voltage is 1100 divided by 3.8, which gives us a voltage of 289.5 volts. Rotor impedance 0.1012 plus 0.25, that gives us 0.25 at an angle of 87 degrees. Then the current will be ER over ZR. That is then 289.5 divided by 0.25. That gives us 1158 amps at an angle of 87.3. Power factor is the cosine of 87.3, which is 0.047. Then for a slip of 4%, then the formula changes from is going to be SER over R plus JSX naught. If we substitute it in the formula, we get 710,125 at an angle minus 42.5. Cosine of that is 0.737 lagging. Then they want the current to be 100 amp in the stator. Now remember, I stator is now I rotor times K, which is 3.8 times 100, which gives us 380. And therefore, the impedance is going to be 289.5 divided by 380, which gives us 0.7618. R2 is the square root of S minus X squared. That gives us 0.7196. And the external resistance is the total resistance minus that of the stator. That gives us 0.07076 ohms. Right, let's do a new share and see. Yes. We have a 150 kilowatt and 3000 volt 50 hertz 6-pole star connected induction motor. Star connected slip rings with a transformation ratio of 3.6. The rotor resistance is 0.1 and phase leakage reactance is 3.6 millihenry. The stator impedance may be collected. Find the starting current and starting torque at rated voltage. So there we have that X is 2 pi FL, which is 2 times pi times 50 gives you 314.2 times 5.61 times 10 minus 3, that gives you 1.13 ohms. Amen. And then R referred is 3.6 times squared times 0.1 is 1.3, and X referred to the stator, 3.6 squared times 1.13, which is 14.7 ohms. Right, in the meantime, when I'm done, I'll put this on your WhatsApp group, so then you can study it with your papers as well. So I stator is V rotor over R rotor plus JSX naught. Substitute, that gives us 116.66 volts at the 85 angle. Synchronous speed is 3000 divided by 3, which is 1000 revs per minute. And the starting torque is 3 times 60 over 2 pi ns V squared R rotor divided by R rotor squared plus R X rotor referred squared. That gives us, if you substitute it in there, you get 513.03 Newton meters. And then you will see with this, there's tutorial problems. Now I'd like you to finish that for next week, and then we'll go on with that. I'll also send you this now. Any questions?
So are we going to submit the tutorial problem?
No, we'll just discuss it and see if you get it right.
Okay, so and just be aware you have 1 minute and 45 seconds left.
Yeah, I know. So do you want some more time, or are we done?
Yeah, we are good, sir.
Okay, guys, enjoy your weekend. Do not drink and drive, and condomize. See you guys.